Modern computing environments project an illusion of impenetrable defense. Beneath the surface, advanced persistent threats routinely penetrate these systems through three distinct vectors: connected cables, ambient airwaves, and intercepted data streams. The defining vulnerability enabling these breaches is the assumption that physical proximity equals trust. Because a device sits on a physical desk or connects directly to a motherboard, the host operating system implicitly trusts its peripheral hardware, the local data buses carrying its signals, and the standard time-based mechanisms used to generate cryptographic entropy. A portfolio of patents authored by former Google engineer R.J. Aguirre models a radically different environment. It assumes a hybrid warfare landscape dominated by highly resourced, state-sponsored actors. These adversaries exploit the proximity assumption directly. They utilize hardware supply chain subversion, acoustic side-channel cryptanalysis, and network-level downlink interception to harvest intelligence from the ground up. Surviving this threat environment requires abandoning legacy architecture entirely. To defend against state-level capabilities, trust must be stripped from the operating system. Security requires decentralizing command and baking mathematical isolation directly into the physical bedrock of the machine. The standard local data bus, such as a traditional USB connection, operates on a flawed premise. It assumes every connected device is benevolent. If malicious actors compromise the firmware of a webcam at the manufacturing level, that camera can bypass the host operating system to initiate unauthorized communication with a network adapter, exfiltrating data covertly. This diagram outlines the first countermeasure. Cryptographic units are decentralized directly into the peripheral edge, embedded within the webcam and network card. Encryption at the absolute edge ensures all data traversing the physical bus is heavily obfuscated. The host only sees ciphertext. This creates a new mechanical problem. If a peripheral's firmware is compromised by an attacker, could that peripheral simply be instructed to use its valid cryptographic keys to attack another device on the encrypted bus? Looking at the internal logic, we see the countermeasure for this vulnerability: a hardware-enforced policy switch, explicitly set to deny inter-device communications. Because this switch is implemented at the physical firmware level, it dictates output independently, mathematically immutable via external bus commands. If an advanced persistent threat completely compromises the host controller, the hardware-level policy holds. The peripheral cannot be weaponized to compromise the rest of the local network. Securing the hardware supply chain is only one layer of defense. Adversaries also extract data by observing the physical environment, using side-channel attacks to measure byproducts like sound or timing. This visualization demonstrates an acoustic side-channel attack. By monitoring the distinct sound profiles and timing of physical keystrokes, an attacker can map audio waveforms directly to specific keys and word lengths. Standard encryption batches these keystrokes into contiguous blocks. The resulting metadata provides enough structural context for machine learning models to drastically reduce the time required to break the encryption. This schematic details the solution. The architecture abandons block-level processing. Instead, a single individual keystroke is routed directly into an isolated cryptographic unit. Every single physical key press generates its own unique, independent ciphertext. This isolation extends to virtual environments. Here, a software keyboard feeds individual key events directly into a client-side cryptographic module before the data ever touches the network stack. Treating each keystroke as a discrete, isolated event mechanically destroys the contiguous metadata patterns. Without that contextual structure, machine learning models are deprived of the data they need, rendering acoustic side-channel cryptanalysis blind. An encrypted bus and event-level keystroke isolation are mathematically useless if the initial cryptographic seed used to generate the keys is predictable. Standard encryption relies heavily on timestamps to generate these seeds. If an adversary has physical surveillance of a target, they can pinpoint the exact moment of key generation, narrowing down the mathematical possibilities. This system architecture replaces predictable time data by harvesting volatile physical parameters. It feeds streams from a device's GNSS receiver and internal digital compass directly into an entropy collection module. Continuous microscopic fluctuations in global positioning coordinates and magnetic orientation relative to true north provide a high-fidelity source of entropy that is impossible for a remote observer to measure or replicate. Even with robust local entropy, data must eventually cross the internet. This exposes the critical vulnerability of modern networking, the standard TLS and SSL key exchange protocols. This flow diagram illustrates the standard key-first architecture. A client and server negotiate cryptographic parameters, and the server transmits the resulting session key over the downlink channel. Intercepting this transmission allows a man-in-the-middle attacker to steal the key and compromise the session in real time. The AGIEP protocol inverts this flow. The receiver, rather than the sender, generates multiple cryptographic seeds and pushes them upward over the uplink channel. To transmit a message, the sender selects a pre-queued seed and applies a key derivation function to encrypt the data. The sender transmits the encrypted message downward. Possessing the original seed, the receiver independently applies the same function to generate the identical decryption key locally. The session key is mathematically derived on both sides of the connection and never actually transmitted over the network. Without a key traveling across the downlink, standard man-in-the-middle interception is rendered obsolete. When these localized defenses and network protocols operate in unison, they form a cohesive pipeline. A single key press is encrypted at the hardware level, travels securely through a zero-trust bus, and crosses a hostile network using inverted, seed-based cryptography. Effective defense against an omnipresent threat model necessitates the removal of implicit trust from every layer of the stack. This level of architectural paranoia requires significant engineering trade-offs. Implementing discrete keystroke encryption introduces unavoidable bandwidth overhead, and decentralizing cryptographic units into peripheral firmware raises manufacturing complexity. However, these upfront costs are negligible when measured against the catastrophic stakes of corporate espionage, targeted surveillance, and the systematic theft of intellectual property. As software perimeters prove insufficient against state-sponsored actors, cryptographic security becomes a physical property of the computing bedrock.